All right. Good morning, evening, afternoon, wherever you're joining from, and welcome to the first sessions of today for NDC Sydney. Today I'm going to be talking about fixing some poor performance patterns in Azure SQL Database applications. A little bit about me before I start. The one bit I kind of like these days is saying that I started with SQL Server way back in the last century, playing about with version 6.5. So I've come through everything and all the evolutions of it, all the way through to the cloud-based stuff that we've got these days. I've been a Microsoft MVP for the data platform for the last 6 years, and SQL Database really is where my expertise and focus has been these days. So really what we're going to look at here, back in the days when you had your on-premises stuff, you've got complete control about where you would set up your application, your database servers. You'll have them put together in the same racks and really close together, all the equipment you need there. Everything would seem to be running really good. You would tend to have these big beefy machines for your database server, so you're probably masking a lot of things that might have been happening there. One of the best examples I had was an upgrade project I was working on. And in the data center, they decided for some reason to put the new database server in a rack on a different floor, so far away from the existing application servers. Now, when we did the testing to turn this on, it just absolutely dragged. There was nothing, there was no response, no throughput. And it turns out, with a bit of investigation on that the cable run length between the application server and the database server ended up being something ridiculous, like about 120 meters. So being able to then change that back, move everything else about into different racks, took a little bit more downtime, but we got it there and put everything together and ran brilliantly after that. But when you go to cloud, who knows what you're going to get with that? You've got no control over the placement of where your actual service is going to be running. You don't know whether your application server is going to be anywhere near your actual database server. So a lot of these things, particularly around how the interaction is and how things like latency are going to impact it, now become things where you have to pay a little bit more attention. And that's kind of some of the focus we're going to go through on this session. We're going to look at some of the bits where you can see the latency being impacted and how we can mitigate for that as well. But the other side of it is also, because you're there on somebody else's infrastructure and you're buying a set amount of power for your database, how do you make use of that to get the optimum performance out of that? How do you squeeze every last bit of performance out of the CPU memory and I/O resources that you've been allocated for the amount you're willing to pay for? So you've got that trade-off there. Yes, you can throw more money at it and go bigger and beefier, but is that really value for your system by going that way? So there's a delicate balance there, and we'll look at some of the ways that we can make sure we optimize for that. I'm going to go through it. I've picked 5 areas out that I think are the most important bits to consider for this. So that's what we'll run through today. So the first of those, Firewall Access, and how you access Azure SQL Database through either a proxy or a redirect. So I go out there and I deal with lots and lots of SQL databases all over the place. And what I normally see is this sort of setup here. You've pretty much got the simplistic approach of your application has a connection string pointing to your SQL Server endpoint. You've got TCP 1433 opened up for that, and off you go. That's all people tend to think of, and all that is there available. What that actually does, though, is it directs your connection to the relevant gateway. The gateway will then go, okay, let me find out where that connection you want to go to is actually residing. So which of my multitude of servers, running SQL Server, running instances there with your database on it, do I need to get a connection to? And it will then proxy that through to there. There is another option, though, where we can get a direct connection straight through. Again, we're pointing initially to the gateway, but what it's then doing is it's doing lookup for us and responding back and saying, well, actually, that particular database is residing here. Let me give you the direct address for it and let you pass through that way. It does require some changes to your firewalls, though. So rather than just having 1433 available for your system, you've now got to open up the 11,000 to 11,999 range, because the redirect will actually take it away from 1433 into this higher port range to give you the direct connection through. So when we look at that, a few bits and pieces, you want to make sure that you've opened up that port range. Now, depending upon where your application server is, there's different considerations there. So if you're running that in Azure, there might be some differences you need to look at there. You might not be coming out of your own network boundaries so much there. So some of the port issues might not be such an issue. But when you're running with Azure and you've got an NSG perhaps on your VNet, again, you've got to consider the additional port range on there as well. Same when using the VNet endpoints as an option to get into your SQL database, and that sort of stuff goes through there as well. The other bit to remember, though, is depending upon your connection to the internet, because you've got your database up in the cloud, if you're still running some of your connectivity from on-premises, where is the actual core bit of the latency there? If you've got a poor internet connection, the gain you get from this might be insignificant, because your biggest pain point is actually your latency between your particular data center or on-premises, your office, whatever it is, and the internet. So a bit of testing is worthwhile doing there and see whether it can actually improve that. It used to be the only way you could change this was either directly through PowerShell or the Azure CLI. It used to be a code-only change to update the connection policy. That's now been changed, and now we made that front and center in the portal. You can go straight now to your database there and actually set that up. And you can actually see that quite easily. If you run a network analyzer on the traffic between your application and the database, you'll actually see that switch over and getting the new address for your database server and passing that back to the application and coming back through on the higher port range there to show that. So, first demo of the day, let's jump in and have a quick look at this. So I've got a VM in Azure that I've just installed Management Studio on. That's going to be my simple client for this particular test. First thing is I'm going to show that on my firewall, so for the Windows firewall, something to consider there if you're running on your application on a Windows server, make sure that your Windows firewall allows you to get out on the right port range as well. So I've got everything open there. I've got 1433 for my first initial connection. I've got my 11,000 port range open there as well. So nothing's blocking that at the moment. If I come in and look at Azure, my connection policy here, I can show that that's now got the various options here for either default, proxy, and redirect. Now, default actually is proxy by default. So if you haven't changed anything, it's going to be doing the proxying there as well. And you'll be able to change that and update the way it goes on the connection there. The other bit that's going to be relevant, if I find my right group here, is going to be on my NSG. And again, looking at my outbound rules, what I've got is I've got 1433 as open, so it's allowed all the time. But at the moment, my redirect group, my 11,000, I've got that set on a deny at the moment. So we're going to block things out from that. So let's jump in and have a look at what we're going to do here. So I've already connected this up, got my connection. Let's just make sure that we're set to the right subscription here. I'm just going to set a few variables for my resource group and everything else that I need to connect to. I'm not going to change my firewall rules here because they're already set up. We don't have to worry about that, but just let's verify what our actual connection policy is at the moment. As we can see, it's still got that set to my default. So for the first bit, I'm going to actually be more explicit. I'm going to say, let's set that to update. Set that to proxy explicitly. And we've already seen that I've currently got a deny on the NSG, so we'll skip that one for now. So let's jump on to my first Management Studio. I'm going to connect on to my database server. If I type my password correctly, that would help. Cool. I'm just going to open a new query. Doesn't matter which database. All I'm going to do on this one is simple query, just selecting a straightforward value back out. So I'm taking away things like any sort of IO interaction from here. It's all going to be this. Just give me something back. I've got this option with Management Studio where I can include the client statistics. And that's kind of useful because when I run this through and let it go through the various runs here, it'll go through selecting this 100 times. Once it's completed that, it's going to come back and give me this bit on the client statistics. An important thing I want to look at here is the wait time on the server replies. And that's the measure of where it's going. What's that latency coming through on my connections here? So, it gave me 250 milliseconds on that. Okay, so we've got a starting point there for that side of it. Now let's open up our NSG. So we're now going to make that 11,000 to 11,999 port range available. And now I'm going to open a second connection here. So same server, same database, same query. And again, put my client statistics on for this one and fire that off. So what we'll see once that comes through is completely the opposite of what it's done for every single time I have demoed this, and is trying desperately to show me a liar on here that it is now changed it to a higher value, which is quite fascinating. Let me come back and rerun on the previous one as well. That is the most bizarre experience on there. So out of probably hundreds of times I've run this demo, it has always come down and showed a reduction in the time on here. I don't know why that's perhaps decided today of all days to give me something bizarre on that. But on the redirect policy, what we should see is that time will come down. If I ran through a number of tests and got this as an average over time, undoubtedly you'd see that, but really just for time on the session today, we'll skip past that. But the experience you should see there from that is that will come down. So again, it's reiterating the fact of don't just do one test. Once you've got this, set it up, run it with a realistic expression of your workload and see whether the two options give you a benefit from there. But that's somewhere where you can start to squeeze some more performance out of your system. Now, related to latency as well, overfetching. So the N+1 selects issue that you can get with your code. Again, with that increased latency that you may well get with a cloud-based system, that's going to increase that issue. So the more round trips that you have to go back to the database, the worse that's going to be for the performance of your application. Very commonly seen in things like ORM applications, or where you've got the use of APIs that are very focused on delivering one particular piece of information back to you. When you start to join those together and go, I need to get something a little bit more, and extends it out with that sort of one-to-many relationship, that's where you can start to see this sort of issue coming in and feeding into your code if you haven't actually addressed it and looked to see how you can optimize for that. So again, you tend to get this bit of your first entity there, you're getting the whole collection for that, and then for each of those having to go and get the related pieces of data that go with that. As I said, another way that I've seen it is various calls to an API that returns a certain amount of the data that you actually need to resolve for your query, but not everything. And then from there, it's going off for each row, querying the additional API to go and get that additional pieces of data, fill in the gaps, and give us the whole picture that we're needing for the application there. So you can see visually that whole approach of how it can then mount up in the number of round trips to the database and decrease your performance overall. There isn't a silver bullet on this one because there's so many ways to code for this. One example here, so changing the simple approach here to use a .include on your call to the object model there. That's one way that can pull everything back from your related items. It may well be on that, though, that you then bring back too much data. So if you're only looking for one small part on the related items, this is still going to pull everything back related to that. So something like this might be a good scenario where you go for an explicit query to the database. So you write your own query, whether that's through a stored procedure or whether you actually physically write out the query and send that as the definition there to go and get that, and it can return everything back in one go from there. Okay, so example around this, and I just got a little bit on this to show a sample of codes. I didn't actually, yes, I did this one. Activate that window. So what we're going to run here, the way we've got this one set up is for the basic setup of it, I'm really just going back to the one object here. Once I've got all my standards, and then going back and doing it for each of those, getting all the related students for that one. That's going to show me my N+1 issue there. One method to fix that, I'm using my include there to pull back the information around the students in this one, so that when we come down to our for each loop here to write everything out, I've already got all the data back for that one. So it's a very simple bit of code to do that. But if we fire that off and show the first version of it. So we see we've got our first query here, and then our second format of the query here for each entity that we've got through on there. We'll find that some of those are giving us some data back. So we get Bill and Steve out the first time, Mohan out the second one, Capel out the third one, and on from there as well. And if we look at the timings on each of those calls for the additional data, that's at 25 to 15, 25 to 30 milliseconds on each of those. So that mounts up in terms of our performance there and the number of round trips. If we fire it off and look at the fixed version, we'll see that our single query, yes, it's a bit more complex in building things out and getting the join in place there to get our child objects, but we get everything back in one go, and we've got far, far less time involved on that as well. So something there to make sure that you're looking for that, trying to see things through that. One of the ways you might be able to pick that out if it's not obvious from your code is starting to look at things like the query plans that are generated on your SQL Server. And looking at the details of what you're seeing in there, you may find that if you're getting an awful lot of similar query plans, but there may be single-use plans or a lot of very, very similar plans, that might be an indication that this is what you're experiencing, because then for each of those child items, it's doing the same query but with a different parameter on it. And depending upon how you're then set up for parameterization and managing your plan cache correctly, that might be something that manifests itself in there. Which leads us on nicely to the next part I want to talk about, is that piece of memory optimization. So the way you get your query plan goes through before it actually starts to return your results. That query submitted, the query text gets hashed first of all, and then it looks for a match for that hash in the plan cache already. So has this query already been run? Do I already know how I'm physically going to go about getting the data and returning it to you? If it is, great, I can just go ahead, use that plan and start to deliver your results back. If not, I've got to spend the time to compile a brand new plan for that, store that into the plan cache, and then I'm ready to go ahead and execute. But there's limits to that. So you've got a fixed amount of your memory where you can actually store your plans. Now, it depends upon the tier of database you've got, so it is something that's scalable. With the higher tiers, you do get more, but it's limited by either a number of plans or the total size, whichever gets reached first. And the hash has to be an exact match to get you the use in there. So be aware that if you've got case differences, if you've got an extra space, if you run things over multi-line as opposed to a single line, all of those can actually be slightly different. So as long as your application is sending it in a consistent manner, great, you should be able to pick things up. But if not, then you might start to get some bloating in there as well. But also with buying a service and the platform as a service approach, you've got a fixed amount of memory to use there and to use it across everything. And your memory shared between your buffer cache, where your data is actually loaded and returned to you. And that's the bit that you want lots of that. You want all your data to be there so that you don't have to do any disk I/O where possible. But the more you're using up for your query plans, the less you've actually got for the actual data. And you've got that possibility of impacting things there and causing more I/O instead of being able to return and satisfy your query from memory. What causes that is a lot of bloat, is a lot of single-use ad hoc plans. And each time it goes through those, it's also consuming high CPU as well, because it's got to recompile or compile each of those new plans as well. So if you start to monitor your performance and see high CPU, high memory usage, you've got less DTUs that are available there for running the actual queries themselves and delivering the results back to you. So again, another little bit there to be aware of how your system's being used, and can I tune it better to give me better response? First step is obviously looking to see, can you actually write your queries in a parameterized version? Can you make use of that within the code to ensure it goes through? And using the correct type of parameters as well. I've seen bits where using the max option, I think that's the default for EF, if you're just using the string, is it will default to varchar max type. That's poor as well, because one, it's got to be implicitly cast and converted at the SQL engine to match another data type. It limits the use of indexes. So again, if you're parameterizing, make sure you're defining your parameters very well, and particularly in terms of the length of those parameters. We can tweak it at the database side by forcing parameterization. So we can say, I don't care what's coming in, I'm going to look at every single query, and if there's an opportunity to parameterize it, I'm going to do that, and I'm going to store the plan cache, I'm going to store the parameterized type. So I will get matches in the future there and be able to reuse it. It does cause a little bit of slowness that way because of the conversion and looking at parameter sniffing. So you might have some impact in terms of performance by doing it that way. So perhaps a better approach is having the optimize for ad hoc. So if you know you're going to get a lot of queries that are going to be in single use type, if it's going to be that variation is going to be small enough and things are then thrown away, then optimizing for ad hoc is a great way to do it, because it won't then store the full plan on the first time. So if you go through and that's never repeated, great, that stores a minimum amount of data and is easier to flush out at the end of the day. It's only then once you get that used a second time does it do a full version of that. So let's have a look at the impact that can have on our system. So what I'm going to set up in my database is two store procedures. And most of it is here for making some randomization on it. So I'm going to just tell it with my parameter how many times to run. What it's going to do is this first bit of code is just going to give me a random value that I'm going to use in the inner select. Now for the first one, the unparameterized version, I'm going to build it up as a dynamic SQL string and pass that through. So a very simplistic approach on there, passing in just the state value and calling exec to do that. The second version of it, I've actually got it properly parameterized in there, passing that in as a parameter variable. And yes, it's a very simplistic example. It's not really something I'll see so much of in the real world as the difference between these two, but it's something that's sufficient to show the differences in what we're doing here. Okay, so we've got those created. First thing I'm going to do is make sure that everything's cleaned out, that we've got a nice clean cache, everything's empty to start with, so we're not impacting it from anything else. And just to verify that, there's nothing in there. And my filter here is just making sure that I'm not logging the actual query that's running to get this data back to actually include in there as well. So let's run the first one. That'll run through, it'll call the store procedure 10 times, get me some data on there. And if I look at what that's done, what we can see is that we've got, first of all, where my cursor has gone to, get back onto the live screen. Doesn't want to come up, there we go. So we've got one plan here for the procedure itself, but then we've got these other 10 ad hoc ones for each time it was called. And we notice on that each of those has a single execution on it. Now, if I go the other way and run my parameterized version, then once that has run through my 10 times, let's go back in and see what impact that's had. Now what we've got is we've added in another one for the procedure, but this time I have an execution count of 10, so it's called the same thing 10 times. We've been able to get that reuse out of it. So I've saved that bit on there. I haven't had to, to bloat things out and increase the number of plans that we're storing to get that done. So again, we're going to come back in, do the same thing again, get our first bit to start with. So we've cleaned it all out. We're back in here at just the basic stuff on here. Now I need to throw the next bit into a new query. I'll grab the bits back from copy those into my new one so we can look at it. On this one, I'm going to run it with forced parameterization. And again, running the unparameterized selects. And what we can see now is it's converted that. It's worked through on that query on the inner select that I can take that bit out for the parameter that's passed in. I can properly parameterize what's stored as the query plan. So we can see the format has changed. We're now passing it as a variable in here in the query text. It's changing the type to be a prepared plan, but we've got our execution count of 10. So even just on that, we can see it has made some improvements in what's going to be stored there, the amount of reuse, and being able to go through things a lot easier from there. Okay, let's reset that back. So the other option I mentioned was optimizing for ad hoc workloads. So again, we'll set that up, clear things out, and just show what we're using in terms of the memory usage on here. And I'm just going to capture that out. Let's just save that in there for now. So I'm just going to pick a value. I've just hard-coded in a particular version in here for that inner select. And let's see what that's done. So we've got a stub of it in here. An important thing to notice is it hasn't actually stored that full detailed query plan. So our ad hoc bit here is just going, what's the absolute minimum? I'm just going to store what's the text and the SQL handle and the hashes, minimum amount here, to manage that. So if I never see that query again, great, that's all that I've used up, is just that small amount of memory to store that piece of information. If I run it again with a different one, again, what I'm going to get is another stub created for that one. Now, if I go back now and reuse the first one and show that, we can now see that it's changed from a stub into full plan and is now stored full query plan details in there as well. So we can see we've got that space saving from not having to store that. But in this case, it won't be a big amount because it's a fairly simplistic query, but you can imagine if you've got a fairly complex query and multi-steps in it, that actual query plan can actually grow to a fairly reasonable size per plan. And that's where we can start to see that will blow out the amount that's used in our plan cache. So if I go back and compare that and see what the changes have been, so we can see that our number of plans have increased, and there's been a small increase in the amount of memory consumed by that. In this stage, about 0.5 megabyte on that. But again, that's for a very small, simplistic plan. We can see that if that was something a little bit more substantial, that could start to grow at a reasonable rate as well. So how much can that sort of get into it? So if we run that another 100 times, I'll come back and look at that once it completes. And looking at that, I think Azure's got a little bit of a slow day, perhaps. So if we come onto that and see what difference 100 executions makes, again, it's not a massive amount on that simplistic one, but if you've got a busy system, it's not parameterizing things correctly, you're starting to get various ad hoc plans introduced on there, we can see that can start to creep up. And depending upon what level we've set for our database tier, then that can start creep into the amount of memory that we're consuming and what's available for everything else to make use of. Related to that, again, now looking at the buffer cache side of things rather than the plan cache, how can we ensure that we're making best use of our memory on there? Compression is something I don't see enough of. It's almost close to having a free hit to improve your performance in this sort of environment. Now, column store indexing, that's one that's just there. By the nature of that and the technology it uses, that's always compressed. It's a fantastic compression level that's in there. It's the same sort of compression that's used with Power Pivot in Excel, with the volume you can get in there. So that same engine is used for the compression on that. And massively compressible, really good. You can't switch that off. It's always compressed by the nature of it. So that's one option you've got there if you can make use of column stores. There is also a compress function. You can actually tell SQL Server to store compressed data, and it uses the gzip algorithm to compress that data and store it into your column. You've then got to deal with that when you're reading things back again, but again, it might be one way of making use of compression to reduce the amount of footprint of your data. Row compression changes a bit on the storage format, so it's quite a simplistic algorithm on that, as we'll see, and it will start to reduce the space per row, giving you more rows per page. Fewer pages overall, again, better use of your memory. Page compression then takes that a step further and actually looks for different patterns on the page to see how it can then reduce that even further. So row and page compression is the one we're going to focus on here. So row starts quite simply. It'll basically go where you've got fixed length fields, can I reduce those by changing them to a variable length and storing them down that way and only storing what's actually needed rather than the full allocation of bytes for that particular data type? Again, I'll look at it and say, if I've got a big int, but all my values are small enough to be in a small int or a tiny int, again, I can do that and reduce the storage available for that. Things like nulls and zeros, they're optimized to take up no space. So we can see on just something as simplistic as this, we can reduce quite a significant amount there on that row, down to over 1 million rows, about 30% of the storage space. It's not a bad bit from there. So page compression, we'll start with the row compression algorithm first of all. So it starts to look in each column for repeated values. So what's common that it can take out and store that as the primary value for that particular row on each page. So, for example, on here, it finds the AABCC part for the first column, and then it puts a code in to say, well, how much of that is used by the actual value? So you can see this uses the first 4 characters and then replaces the next one. The second row has an exact match, so it just takes everything back there. It doesn't have to store anything from that one. The third row here takes the first 3 out of our code value and then adds the rest in there. So you can see it starts to remove some of the parts out from there. Once it's done that first bit across the rows, it'll then start looking for common patterns across the entire page. So again, what we've been left with here, the 4B and 4B, we can say I can store that once and just index it through those to say what value should it be taking on there. So those repeated values are removed as well. So because we get more rows stored per page, every single page that's in the buffer row has got more data, more rows, and quite easily based upon that. So there's fewer reads to satisfy a query. Now, whether that's logical reads or whether that's going down to physical reads by pulling it back from the disk, fewer reads is better because IO is generally always going to be the slowest part of our system. We get more pages fed in, so they're possibly going to stay there in memory longer as well. So the flush out algorithm that goes, what's the last page that hasn't been touched? If I need to bring more data into memory, that's what's going to go first of all. And there's a measure of page life expectancy, which is how long are you likely to get that page to stay in memory without having to be flushed back to disk and go back in again. So that can get us to having higher values on that. The trade-off is, because it's got compression on it, because we've got those encoded values effectively, it adds a few more CPU cycles to then be able to translate that back and forth while it does that. From my experience, the CPU overhead is really low compared to the value you're going to get by being able to keep more data in memory and read it back from there rather than having to go for IOPS. With some caveats, so understand your data before you decide to go down this route. The workload metrics really will give you that indication of which type of compression you really want to consider. So if you only get a few duplicate values, you probably want to look at row compression because you're not going to get much over the page as it pulls things out. And then the type of operations that you're dealing with. If there is a high percentage of updates, page compression is probably not going to be the best there because it's going to add a lot more CPU overhead in that case. And even just the type of table access that you've got. If there's a large number of scans, so you're looking over ranges for most of your queries rather than singleton lookups, page compression again is going to give you some good returns on that as well. You can compress heaps, but they won't actually do the compression until you rebuild those. And the way you rebuild a heap is to put a clustered index over it and then drop that clustered index again. It will reformat things on the heap, it will tidy things up. It's a good thing to do occasionally anyway, to get rid of forwarding pointers and things like that. So it tidies up your heaps. The non-clustered index does not automatically inherit the clustered index compression settings. You have to be explicit on that if you want it there as well. And you can't do it for lob pages. So a few bits and pieces around that, some caveats, but if you're planning this well ahead, it's something that will give you good value from there. So let's have a look at some of the bits around this. So one of the other bits with Azure SQL Database, they haven't put all of the internal functions across. There is on your on-premises, your full-blown version of SQL Server, there is some functions and procedures that you can run which will give you an estimate directly of the expected savings if you switch compression on. It's got a test to make sure it is a specific version, which they haven't unfortunately updated yet, to include the version type for Azure SQL Database. But Cairney Delaney's hacked that apart, done the changes, and created an equivalent set which works in Azure. So I'm going to make use of that one to give me my estimates from here. So what we're going to do is I've set up those objects to do my estimates. I'm just going to go through now, and on this particular database, I'm going to run that through and say, give me an estimate of what we can actually get with the various types of compression. So what is going to be my space savings overall? So how much more data am I going to be able to bring in to the buffer pool based upon setting compression on from here? Now that might take a minute or two to run through, so we'll leave that in the background and actually look at the next part of the demo as well while I'm doing that. So how I'm going to show you this is I'm going to gather the ION and time statistics as we go through it. And it's just going to be basically selecting from a single table within the database here. If I clear some of this, I'll actually see when that other query has finished running as well, which will be useful. Still going, okay. So the first bit here is not going to be impacted. I'm going to get my select from this one table here. And that'll take a few seconds. It's a reasonable sized table to go through. We're definitely having a slow day on Azure by the looks of it. Okay, so the important things I'm going to grab out from here and keep a note of. Just the number of logical reads and the execution time for that as the plain version on here. That's still going. But we'll go ahead and rebuild this table. So we're adding row compression onto the table first of all. So it's just going to go through, run that on each of on that table. Once it's got that, we'll just rerun the query again to get the same stuff back. Okay, so we've now got this row compressed. So we should be somewhere around about the 10-second mark to run this one through. He says as it passes through 15 seconds. Yeah, we're quite high that first time there. It's almost 30 odd seconds. So okay. So what we can see immediately is the number of logical reads has come down a decent percentage there already. And if I look on the time values, we've had a little bit of increase on the CPU time, so that's related to that part of how much effort it's got to do to actually do the decompress as it comes out from memory there. But overall, because of the fewer amount of reads that we've had to do, we've come through in a much quicker elapsed time out of that. So we've got the benefits there. Yes, there's a little bit more in terms of effort on there, but the benefits out of the IOPS has certainly been worth it in this scenario. Now let's look what happens if we go to page compression. This one's now complete, so we can see here that my expectation, if we go to page compression on here, is going to give us, we're going to reduce down to 83% of the original size of the database. So, almost a 20% saving in terms of how much we can consume. That's obviously going to get a significant amount more data into the buffer cache, which is being reflected in as being able to get far better query response here as well. So once we've completed that compression, let's go ahead and run our query again, and let's see what benefits going to page compression is going to give us throughout this as well. So we were 28 seconds for the previous one with row compression. And we should come within that, or similar time. So again on there, once again, we've still reduced the logical reads even further. Again, a slight uplift on our CPU time on the server. But again, we've had some gains in the overall performance. So that ability to reduce how much I/O we're actually doing is more than overcompensating for the increased CPU that it's touching whenever we deal with that. Okay, and the last section, and it's one that that I found was really quite buried in the documentation. It wasn't something that was the most obvious to me to work out what was going on in some things until I started digging a little bit deeper. But once again, that bit with ensuring that things are well behaved, and ensuring you get the service that you're paying for, there's got to be that limit around everything your SQL database does to reduce the noisy neighbor effect. So there is IOPS limits as well. So as well as you're only getting so many CPU cycles, you've got so much memory. There's that bit around I/O, and it's applied to all the I/O. So just your regular storage of pulling the pages back off disk to read into the buffer cache, that's all part of it. Your transaction log as well has got that. And we can actually see what, for each tier of database, we can identify what the particular resource limits are for all those. It does split up between internal and user workloads. So your internal workloads are well managed and controlled by a completely different pool and given different resource limits. But as a user and what you're setting your application to be able to use, that's done separately from there as well. Although that is the target of it, you may not get that full amount just because of additional limits in the underlying storage. So where you've got an amount of shared storage, because what everybody else around about you is doing, if it's all hitting at one time, yeah, you're going to have impacts there at the physical side, which is going to reduce what you're going to get. But the expectation is you should get pretty close to there. And the one I've seen with the biggest impact has been the transaction log rate governance, and it's hard. it's a value that will be throttled while it's happening. So it's not something that goes, oh, you've overstepped your limit, I'm going to reduce you now. It will actually slow things down as it's going through into the transaction log to maintain it within the limits that you have available. So large I/O type queries are the ones that are going to have the biggest impact there. So things like bulk insert, index builds, all of that, when it generates an awful lot of transaction log activity, are certainly going to be limited through there. We can monitor for that, though, so we can look at what's happening at a point in time, seeing what the weight stats tell us about what's happening there. Are we seeing this particular weight? And some of the ways we can get around that is maybe looking at what sort of pattern we're using. So if we're doing a load for staging, and then we're going to transform that into the final tables, then rather than loading that into our database, think about loading it into TempDB. It's minimally logged in there, so you won't get the same throttling rates hitting. There'll still be some part of it that will cause that, but you won't get it to anywhere near the same rate because it doesn't log as much to start with. And then when you extract out of there into your database, you put things into the final versions, you may well have small queries that you're able to do that with. You may be able to batch it through there in some ways to improve the performance. There's a lot of ways you can improve that sort of pattern. If you've got tables that you can use a column store indexing with, then loading into that bypasses it as well, because the compression it puts in by the nature of the column store index is going to reduce the log rate as well through that. But that does increase the CPU. Again, there's all those trade-offs there. But the important thing is that this 96 megabytes per second on the vCore instances of Azure SQL Database is an absolute hard limit. You can get slightly above that if you go to the hyperscale tier, because it uses a different mechanism for the transaction logging there. You can increase that up into the hundreds of megabytes per second. All right, so let's have a quick look at what we have. So my database here, we'll pay attention to this as we run some of the queries through, but I'm also just going to bump one of these instances up before we get started. I've got them both sitting at the same at the moment, but let's push this one up to a higher tier level. Okay. So on my basic one, we can see, and these are my log rate DB and my log rate DB max. They're identical databases. The only difference is going to be the actual performance tier on those. So that's going to show us it for there. If I start a new query for this one, and hopefully it has completed the scale up. It's still in progress. We'll see what it reports. Grab the same query. Not yet. It's still waiting to scale up on that one. We'll come back and we'll show that we'll see the difference there on the rate values by scaling it up from the P2 to the, I think it's P4, P6, or S6 rather, that we went to, not the Ps on this one. So a little bit of a workload that we're going to run through here. And all I'm going to do is, ultimately the workload is just taking a copy of one table into another. So using that select into. And what I'm going to monitor through this is my weight stats values, so we can see what the biggest weights are when it runs through on this one. So I'm just going to run this one through on the first database. And while that's doing that, I'm going to take a new query here as well. And I'm going to copy that so we can run this in the second database to see the difference as it goes through from there. So this will take a few seconds to run through and bring you back the details. Clear out the rest of these if it wants me. Oh, save anything in that one. Okay. So what we can see is it ran through here. My log rate governor was the biggest weight. And out of an execution of 44 seconds, I've got over 40 seconds of accumulated waits. Now, that's not meaning that the actual query only took a couple of seconds. Because it went into a parallel query, this is added up from all of the threads as well. So it's not necessarily saying that that whole percentage of the entire query was all waiting for something to happen there, but there was a significant amount of waits from that. So you can see that this one most certainly was throttled as it went through into the our query on there. That has my so we've now scaled up, excellent. So monitoring on this one. So this is now on my max one. And what we'll do is we go through on this one and run this. What we'll find, obviously by scaling it up, it's going to be significantly quicker as well. But we'll also see quite a different picture on it with the usage of the log rate governor on here as well. Should be on here. So as we can see, it's a far lower percentage overall out of this. So where we were up at 98%, yes, we've dropped a bit down to 96%. As we scale that up, we'll see that come down further and further as well. And if I look at the patterns that we're seeing on here, we can still see that on my log IO percentage, it still did get up there and still maxed out. So there was still weights on it there. It was still pushing it through. For those sort of high IO stuff, there's ways we can start to pull that down. So it's again looking at that and finding out if that's a common pattern, then have I got the right performance tier for my database and anything I want to flick up to there. Cool. So that covers everything from there. As I said, lots and lots of demos through there.